Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next problem number 32. Okay, fluid mechanics, problem number 32. Black smokers. Black smokers are hot volcanic vents that emit smoke deep in the ocean floor. Many of them teem with exotic creatures, and some biologists think that life on Earth may have begun around such vents. The vents range in depth from about 1500 meter to 3200 meter below the surface. What is the gauge pressure at a 3200 meter deep vent? Assuming that the density of water does not vary, express your answer in pascals and atmospheres. Dear students, we need not to make a picture of this situation in mind. We should focus on the data provided in the problem and data required to be found. Okay, so what we have to find out? We have to find out pressure, gauge pressure. Okay, number one. Number two, we have to express that pressure not only in pascals but also in atmospheres. Okay, so for this purpose we will use a conversion factor. Moreover, dear students, here the question arises which density we should assume we should take. Here, because ocean is involved, so we will take density of sea water from table of densities. Okay, these two things are of basic requirement. Remaining portion of the problem depends on the formula or expression involved for the purpose of reaching our desired solution. Okay, so first we move towards two tables. Okay, one table will be of densities, in which we will see that density of ocean or density of sea water. What is the density of sea water? Okay, which will be applicable to ocean. Okay, secondly we see a conversion factor which relates pascal and atmosphere. Okay, dear students, this is the table of conversion factors. Okay, from here we will convert pascal into atmosphere. Okay, 1 atmosphere is equal to 1.013 into 10 raised to the power 5 pascal. In other words, 1 atmosphere is equal to 101300 pascal if we exclude this 10 raised to the power 5. Okay, one thing. Other thing, table of densities. This is on the left column, row number 1, 2, 3, 4, 5, 6. Okay, left column, row number 6, sea water. Density of sea water is 1.03 into 10 raised to power 3 kilogram per meter cube. If we exclude 10 to power 3, then we will write as 1030 kilogram per meter cube. Okay, I think both these tables which we have shown, we have chosen the data which was required from these two tables. Okay, now we move on to our solution in a formal manner. Okay, for this purpose we will have to define a situation. We know that the pressure in a fluid at rest varies with depth h in the fluid according to the expression P equal to P naught plus rho GH, equation number 1, where P naught is the pressure at H equal to 0 and rho is the density of the fluid assumed uniform. Dear students, actually this wording has been exactly copied and pasted from the book. Okay. So we cannot reduce high authenticity of this expression or formula which is going to build foundation for our solution of the problem. Okay, what I have said that this wording has been exactly copied and pasted from the reference book, and so its authenticity is beyond doubt. It is highly authentic. Next we will just put the values. Density rho we have already discussed from table of densities that we will take density of sea water. G is a constant of acceleration due to gravity, 9.8 meter per second square, and H is also given. Okay, now rearranging equation number 1 as P minus P naught equal to rho GH. Okay, here if we shift P naught on other sides of the equation or equality, it will become P minus P naught. Okay, P minus P naught equal to rho GH, and assuming rho equal to 1030 kilogram per meter cube sea table. Okay, sea water, density of sea water, G equal to 9.8 meter per second square and H equal to 3200 or 3200 meter. This is also given in the statement 32 meter deep. Okay, so next only simplification, P minus P naught equal to this. Okay, three values only, rho GH. This is the value of rho, this is the value of G, this is the value of H. Okay, all these three values will be multiplied. Okay, so what we will get, what will be cancelled out, m into m square will be subtracted from m cube and simple m will be left in the denominator, and our resultant value will be in terms of kilogram per meter second square. Kilogram per meter second square. These three quantities when multiplied will take the form this 32300,800 kilogram per meter second square, and we know that as per definition of Pascal pressure is defined in terms of these three values, that is kilogram per meter second square. Okay, we can also write Pascal in terms of Newton over meter square, etc., but directly we know that this factor kilogram per meter second square is equal to Pascal. So our result has become equal to, gauge pressure has become equal to so many Pascal. Okay, next what we have done, we have used that conversion factor in which it was shown that one atmosphere is equal to so many Pascal. So when one atmosphere is equal to so many Pascal, then 1 Pascal will be equal to 1 over divided by so many Pascal and let us here, okay. Dear students, 1 atmosphere is equal to 101,300 Pascal. From here, 1 Pascal will be equal to 1 divided by 101,300 atmosphere, okay. So when 1 Pascal is equal to this, then so many Pascals will be equal to this multiplied by this, okay. So we have applied this technique, and this Pascal has been converted into atmosphere ATM, and this has become equal to 318.86 atmosphere, okay. This is the required solution of this problem, okay. 318.86 atmosphere. We were required to find out the gauge pressure not only in terms of Pascal but also in terms of atmosphere. So we have fulfilled this requirement. We have found that pressure not only in Pascal but also in atmosphere, okay. In terms of Pascal, it becomes equal to 323,00800 Pascal, while in terms of atmosphere it becomes equal to 318.86 atmosphere, okay. Next we have discussed this table. Of densities. Next reference, okay. Sears and Zemanski's University of Physics with Modern Physics. Hug D. Young, Roger A. Friedman, A. Lewis Ford. Its publisher is Pearson. Its 14th edition having been published in 2016, or 15th edition having been published in 2020 has been adopted or followed. It's chapter number 12 under title Fluid Mechanics is our concerned chapter, and this problem has been enumerated at serial number 8 of the exercise given at the end of this chapter, that is to say exercise number 12.8, and this is the end of our problem.